South Florida. We're going to be talking today about an OSPF basic configuration, and you're going to have some fun as well with me. I hope that you enjoy it and keep on with this CCNP route class. Have an excellent day. Bye guys.
Hello guys, this is Victor from Florida, and today we are gonna do something very exciting. We're gonna be working in a basic OSPF lab. We're gonna be doing that on GNS3 equipment. We're not gonna be using packet tracer because it has limited functions. We don't want to use real equipment because I want you that you see this graphic like the one that you see right now. So basically you can understand this concept because we're going to be working basically with this graphic and this topology, and I want that you mentally know what we are doing. Got it? Excellent. So these are the values that you see over here. The original lab was based on a Cisco Network Academy lab, the one that you see over here. It's very simple. And these are the values that you see over there. It's going to have only an area 0. Basically, this is the objective that they have. I made some modifications, so it's going to be more simple for you. So for you to understand this process is going to be way easier as well. So it's going to be a lot of copy and paste. So in the future, I urge you that you try to do that on your own. So let's start jumping on the water right now. Let's see what we can do. Okay, this is the topology that you previously saw. These are the objectives. Configure a single area OSPF on a router. Well, as you could see, it was the area 0 that I mentioned before. Advertise the loopback interface into OSPF. That's when we're going to be setting up the OSPF protocol. Verify the OSPF adjacencies. That is one of the parts that I enjoy the most. So you're going to see how it is loading on one router from another router. Verify OSPF routing information exchange. Modify OSPF link cost. That's to make one the DR and the other one the Bdr. Change the interface priorities. And utilize debugging commands to troubleshoot the OSPF. Background, we're going to be doing this for the engineering, marketing, and accounting department, as you can see over here. We're not going to be using Gigabyte Ethernet. We're going to be using fast Ethernet and serial cable. We're going to start doing a copy and paste as I mentioned. We have a loopback already on it. And we are going to be applying this stuff over here on our GNS3 lab. So to make your life way easier, we did a little bit of the configuration in loopback 1 engineering department, and we're going to be copying the initial values to put on the interface. And basically we are talking over here about the loopbacks and the fast Ethernet 0/0. So here, jump over here, copy, paste, boom. Easy, guys. I didn't have to take about 10 minutes typing the configuration for that. Nice and sweet. Don't you think so? Or at least that's what I think. Okay, let's start jumping on the second one. Trying to make your life way easier. By the way, all this information is going to be over here at the bottom, so you're going to see the link so you can download this lab into your computer. Do that over and over, so eventually everything is going to sync on your mind how everything was supposed to be done. Same thing over here, copy paste, boom, easy, isn't it? Great. Write down all the information. And by the way, I'm assuming that you already know a little bit of packet tracer or you have been working on GNS3, so this process wouldn't be that hard. Got it? Because otherwise it will take me another lab only to explain this kind of stuff. We saw all the configuration over here, how everything came up. So everything is nice and sweet over here. Right now, let's start checking the values on R3. Let's say stop. Copy. On R3, we're gonna check on console. Paste. Sweet. Isn't that right, guys? Excellent. As you can see over here, everything is up, and I am very happy because of that. Excellent, guys. So let's check on our exercise. So far, so good. Leave the switch in blank configuration, blah, blah, blah. By default, all switch port and VLAN 1. We already know that, guys. And are not administratively down. Okay. Configure the serial interface on R1 and R2 with the IP address showing the diagram, the ones that I show you guys, remember. Clock rate commands were needed. One more thing, when they are talking about the clock rate, they are talking to this value over here, the DC on serial 0/0. Remember that we only put over here, we're only using only 2 zeros instead of 3 zeros over here. So on that serial is what our clock rate is gonna be, the same thing than our DC that you saw in the graphic. Got it, guys? Hopefully you do. So on R1, we're gonna do the same process. On R2, it went very well. So everything is good, everything is successful. Over here, the bandwidth, we set the bandwidth on both sides, 64. Usually you use 128 or 1544 kilobytes per second. And the next command is verify that the appropriate interface are up and you can ping across each link. Okay, let's check it out. We already checked that everything was up. As you remember, guys, when we were saying up. So we don't need to do that one more time. And we need to check if we can ping across each link. So let's do this. From R1, I want to ping R2. So this value over here, exit, you see over here, and we're gonna do ping. Everything is 100%, and I am very, very, very happy. Remember that before do that, you need to be on, I put do ping, so it means that it's one level down. I think it wouldn't be in privilege mode. So let's do this. I know that it's gonna be the same thing on R3, so I don't want to waste your time. So far, everything is successful. Great, guys. Over here, add physical interface to OSPF. Enter OSPF configuration pro using the router OS process number command. In our case, guys, we're gonna be using number 1. So what they are telling you over here, router OSPF number, we're gonna be using router OSPF 1. And over here, they are talking about Part B app interfaces with network address wildcard mask area some value command. What they are talking very specifically is this part over here, network, the network that you want to add. Let me show you really quick, guys. This network over here, 10.1.100.0 and 10.1.200.0 as well. They want to add over here this value with 255. Where the number is coming over? That is coming from the subnet mask. This value over here that you could see minus the subnet mask that you have. For example, in this case, if I have a CIDR 30 that corresponds for a 252 subnet mask, the wildcard mask that you're going to be having is this part. Got it? Okay. Hopefully you do. You understand how to subnet. So this part over here, now that we understand everything over here, we're going to do some copy. And we're going to apply this on router 1. So far what we did, we put the network protocol on. And in our lab, we're going to use this part over here. We're going to debug OSPF adjacencies, as you could see over here. So we're going to start the debugging process on, and it's going to start checking the adjacencies that it can have. Let's go back to R1. It's on, as you could see. Adjacency means like the neighbor that you have. And now on R2, we're gonna do the similar process. And when we do this, let me show you something very interesting. What's gonna happen on R1 as well and R2. Each one is recognizing each other. This is now on R2, there is an OSPF adjacency and the process 1 that we just mentioned over here. It's telling that 10.1.1.1, and remember which one is that guy. That was the router 1, is your neighbor. It discovered an adjacency. That's on router 2. And let's check on router 1. Everything is coming up as well. Something very interesting is happening as well. It start the election of the DR and the Bdr process. And we're going to be talking about that in a second, guys. 10.1.2.1 and the DR is 10.1.1.1. Bdr is 10.1.2.1. So what numbers are those? Let's double check that right now, guys. It's mentioning that this one is going to be your Bdr, and this is going to be your DR, your designated router, and your backup DR. So the information is very useful. Now let's check what's going to happen on R3. And let's put over there as well R1. Now R1 is reading what's going to happen on R3. You see this, guys? And let's check over there on R3 what's going on. OSPF adjacencies is mentioned that it recognized neighbor 10.1.1.1 and 10.1.2.1 that correspond to router 1 and router 2. This exercise is coming nice and sweet. Don't you think so, guys? It's like a game. Love to be playing with this stuff, guys. Now, a good part of the exercise is done. Observe the output of R1. When you finish thorough of debugging on R1, okay, we can do that. So debugging is off. So the next question is, what is the advantage of adding network with a wildcard mask instead of using classful network address? Oof. Well, I would say that sometimes a router can be working inside of a major network. A major network start different interface can be involved with different areas. So the wildcard mask will be assigned to each one of the interface for each one of the areas. That's the importance of having a wildcard mask on the router for each one of the areas, guys. Because when you give the control to the interface using the wildcard mask to have up to the very specific area. Hopefully this is going to be an explanation that you can understand, but you already done this exercise and you saw it. In this exercise, by the way, we have been only working with area 0, but you're gonna see in the future how we're gonna be working with a lot of different areas and a lot of different LSA where this information is gonna be very important. This is the basic one, but when we start jumping on the advanced one, you're gonna see the real importance of that. So the next part of the exercise, use the OSPF show commands. Okay, let's do that. What they're talking about. We're going to be talking about the show commands over here, guys. First of all, so you're going to see a couple stuff, and we're going to be jumping, and we're going to be talking about a little bit about each one of them. On this exercise, on R1, we're going to see show IP protocols, and we're going to see the process, the router ID, and the network OSPF. Let's double check really quick. R1, bam. What do we see over here, guys? We're gonna see the router ID number, and it's routing for the networks 10.1.100.0 and 10.1.200.0, the ones that we already applied. And we see as well the welcome mask and the area 0. Remember that we don't have any other area so far. This is the distance of 110. That is the default one that we use on OSPF. Now let's start jumping on the next command. Show IP OSPF. Okay, let's start doing this right now. So what do we see over here? Let's check the values. Over here we can see after this result routing process that is called the OSPF 1. Remember that this is the one that we call, and the ID is this one. Even though that we haven't set that up and we haven't mentioned, it automatically select the highest IP number on the loopback. So remember that, guys. So let's start checking the next stuff over here. C. Show IP OSPF neighbor. Okay. Over here, there is something very interesting. It can read the other router from router 1. It can see router 2 and router 3. And this part over here, DR other. What does that mean? if we have the BDR and we have DR other, that means that you probably is gonna be the DR, the designated router, and the DR other is not either one, the one that have the actual table. So after checking this information of show IP OSPF neighbor, what do we see over here? We can see important information: neighbor ID of each one of the other routers, the state of each one of them, the priority is set to 1 over here, guys, something that we're going to be working in the future, the address of each one of them, and which of the interface they are we can reach them from. Over here, the state of each one of them say that router 2 is the BDR, the other is the DR other, so you're probably gonna be the DR because that one is missing. Remember that if OSPF take the information and put it on the DR and BDR when all the routing tables are located. So the one that don't have to key that is a DR other. So if you have the BDR and you have the DR other, that means that you're probably gonna be the DR as we saw previously, because it choose the DR as the IP number, the lowest, with the lowest IP address on the loopback. Remember that, guys. Now, as you see over here, a variation of this command is this one. For example, and over here you're gonna have similar information. For example, the fast Ethernet is up, the line protocol is up as well. Remember that they were asking that previously. The internet address that we are using, the area 0, remember that you are only using one area, the process ID number 1, that is very important for the selection between the DR and the BDR, the router ID, the network time is a broadcast, and the cost is 10, and it's coming by default the cost. Priority 1, everything. The designated router that we were previously be talking right now is over here, and the backup router that we were talking about as well is over here. You're gonna be checking on this command as well. Over here you see that from R1, on the fast Ethernet, each of them will be the DR, that's the state, and point to point network communication, that's what they have over here. We're gonna have area 0 in both of them, and we're gonna have a cost by default of 10 on the fast Ethernet. Remember that, guys. Now over here, show IP OSPF database. Boom. What do we see over here, guys? This information is kind of interesting. Over here you see the different LSA, the different types. You're gonna see we only have area 0, we only have one area so far, but we can see different states and different area as well. So we can see the different IDs, ID numbers from each one of the routers, and some important information as well. It obviously gets bigger and a little bit more complex once you put a couple routers over there in the network, so it's get a little bit more interesting as well. This is the process ID that we mentioned before. So we have a lot of very useful information, as you could see, guys. So let's start jumping on the next part of the exercise, adding a loopback interface to OSPF. So we're gonna start jumping over here on the first and router number 1, because they are not advertising the routing process yet. We're gonna put show IP route on each one of them. /24 over here. On R2, the same, a similar process, and on R3, Control C, we saw a similar stuff over here. Got it, guys? So we apply this stuff on each one of them. For each router, the only loopback address displays locally connected one. So the locally connected ones are loopback 1, 2, and 3 that we previously saw. Now let's apply the OSPF protocol on the network. I wonder what is going to happen now. This is R1. This is R2. And this is R3. Verify that this network have been added. Okay, I can do that. So let's start jumping right away. Show IP route 32. Why, guys? Why is showing a 32 over here? So this is advertising host route instead of network mask. So let's double check this right away. So what we see over here in show IP OSPF interface is advertising the loopback, and it's not advertising the network mask. So let's start fixing that situation right now, guys. So we're gonna change that behavior right now. We did the router 1, loopback 1. Now let's start jumping. on router 2. And let's finish this stuff on router 3. Let's check the results on R1. $24 again, guys. Excellent. We don't see the 32. So far, this exercise is coming nice and smooth. I am very excited that you're having a good time with this, because I certainly am. On this exercise, we're gonna start jumping on step 5, modify the OSPF link host. The deployment administrative distance on OSPF is 110. When we're talking about EIGRP, it's gonna be 90. On the fast Ethernet, the default cost is gonna be 1. But we are not using right now a gigabyte Ethernet that is way faster than fast Ethernet, but the default cost is 1. But there is a one command over here that we're gonna be using to apply a cost to that process over here. For example, IP OSPF cost value of 50, for example, on this interface. So let's start applying that stuff in each one of the routers that we have, guys. IP OSPF cost of 50 that we are applying right now. Same thing on R2 and R3. Excellent. We did it. This is what we were talking about. The fast Ethernet have a cost of 1. The same thing as the gigabyte Ethernet, in case that you're gonna need that reference in the future, guys. Over here, we're gonna see auto cost reference bandwidth. How we're gonna use it? For example, you're gonna need auto cost reference bandwidth, but you're gonna put the bandwidth that you're gonna need. For example, in this case, 1000 megabytes per second. This value we're not gonna apply. It's only gonna be used as a reference, guys. Okay, got it? Understand? Excellent. So in step 6, we're gonna see how to modify the interface's priority to control the DR and the Bdr selection. For that stuff, we're gonna be checking and show IP OSPF neighbor details, as we could see over here. So we're gonna be changing the priority over here, IP OSPF priority 10, and after that we're gonna see show IP OSPF neighbor detail. So let's apply this on each one of the interface. On R1, on R2, excellent. Now on R1, we're gonna do what we mentioned that we were going to do previously. If I do that, I need to put do first, so it's one layer down. Now we see over here a couple of changes. The priority that we already saw before and already mentioned to you that was 1, it changed to 5. DR is located over here, and the Bdr have changed as well. You got it, guys? Remember, do you want to check the values again one more time? Certainly you do, because I don't want that you have any kind of confusion. these are the values that we were talking about. Over here mentioned that 10, that 1, that 200, that 2, it became the Bdr. What is that located? 10, that 1, that 200, that 2 over here, guys. But besides that stuff, it mentioned that on the neighbor 10, that 1, that 3, that 1, the neighbor priority is 1. Remember that that's how we set up from the beginning of this exercise. Got it? Okay. To make a router take over SDR, use the clear IP OSPF process. They're talking about the spanning tree and the switch, and I don't want to jump on that because we are talking about CCNP route. What is the purpose of DR in OSPF? What is the purpose of Bdr in an OSPF process? Well, guys, the election is made on the router priority. Remember that the router priority is number 1. Once the election occurs, all the routers updates from the DR order, they are forward to the DR or the Bdr. I mean, OSPF maintain an equal picture on both of these routers, the DR and the B on the back of the designated router. Once the backup designated router, the Bdr, is gonna maintain it, and it's not gonna say hello updates unless that the DR fails. DR and Bdr serve as the central point to exchange routing information, guys. If for any circumstances the DR goes down, the Bdr promotes itself as DR immediately. Got it? I hope that you would understand this process, guys. So let's double check. What else do we have? Change topology change. OSPF, like many link state routing protocols, is reasonably fast when it comes to convergence. To test this, send a large number of pings to R1 loopbacks. Okay, let's do that. It was a successful, guy. From R3 we can ping successfully. Excellent. We did trace route as well, and everything came very fast. We're gonna do a small exercise over here from R3. Nice, isn't it? Now let's try on R1. We're gonna shut down that. So now we shut down. Look at the behavior of R3. Do you notice that some packets were dropped, but then the ping started returning again? Of course. You see this guy over here? Over here, he dropped, and he started running again. happens because of the convergence. It looks an alternative route to get to R1, besides the fast Ethernet 0/0 that we mentioned previously. Isn't that sweet? It is pinging again one more time. And the last question, how do you think OSPF convergence compares to other routing protocols, such as RIP? Well, RIP has some limitations. RIP can only do 15 hops by default. Besides that, OSPF can handle VLSN, that is variable subnet mask. With RIP version number 1, it doesn't allow VLSN. OSPF can do a faster convergence because of a faster calculation algorithm. One more thing that I want to explain you guys is that OSPF can be working very good in a small and very well in large environment. RIP doesn't work quite like that. What about EIGRP? EIGRP, I think, is the fastest one, and it was extremely made for large environment. So when you have thinking about the network that you're gonna be using, at the moment that you're gonna be using the protocol OSPF, RIP, or EIGRP, this is something that you really need to focus and put some values on that. One more thing that to remember is the EIGRP is the fastest because it can save all the routes, not only the best route possible. So it can have a faster convergence. Well, guys, this exercise is done. I hope that you like it. In case that you have any questions, I know that it could be a little bit complicated, especially for the beginning, but it's quite interesting as well how the OSPF how we saw to do the fastest convergence through an alternative route than from router 1 to router 3. Guys, I hope that you like this exercise. Please join me in the other exercise as well. In case that you have any kind of questions, please write it down over here, and I'll be more than glad to help you out with that. Have an excellent rest of the day, and keep in touch, guys. Bye.